Question 12, Part E. The points P, 2AP, AP squared, and Q, 2AQ, AQ squared, lie on the parabola x squared equals 4ay. The focus of the parabola is S, 0, a, and the tangents at P and Q intersect at T, a times P plus Q in brackets, APQ. Do not prove this. The tangents at P and Q meet the x-axis at A and B respectively, as shown. Part 1. Show that angle PAS equals 90 degrees. The equation of the parabola is x squared equals 4ay. Rearranging this equation to make y the subject, we get y is equal to x squared over 4a. Differentiating y with respect to x, we get the gradient function y dash equals x over 2a. Now we can use the gradient function to find the gradient of the tangent to any point on the curve. We're interested in the gradient of the tangent at point P, and point P has x coordinate 2AP. So the gradient of the tangent at point P is given by y dash equals 2AP over 2a, which simplifies to the parameter P. We'll call this equation number 1. Now the equation of the tangent at point P is given by the point gradient formula y minus y1 is equal to m times x minus x1 in brackets. Now the y1 in this case is the y coordinate of point P, which is AP squared. The m, which represents the gradient of the tangent, is the parameter P, and the x1 is the x coordinate of point P, which is 2AP. Next, we need to find the x-intercept of the tangent that we just found here. And the reason for that is that that corresponds to point A. Now the y coordinate of point A is 0, given that point A sits on the x-axis. So letting y equal 0, we get the equation negative AP squared is equal to px minus 2AP squared. And we get this by expanding the right-hand side here. Now what we want to do is solve for x, this equation. So we can add 2AP squared to both sides of the equation in order to collect like terms, and we get AP squared is equal to px. Dividing both sides of the equation by p, we get x is equal to AP. Now this is the x coordinate of point A. Now the gradient of the interval AS can be found using the 2-point gradient formula, y2 minus y1 over x2 minus x1. So we have 0 minus a over AP minus 0, which equals negative a over AP, which simplifies to negative 1 over p. We'll call this equation number 2. Now from equations 1 and 2, so we're going to take this parameter here, multiply it by negative 1 over p, let's see what we get. P times negative 1 over p is equal to negative 1. So if we're multiplying two gradients and we get negative 1, that implies that the angle between those two gradients is 90 degrees. So this means that AP is perpendicular to AS, therefore angle PAS is equal to 90 degrees. Part 2. Explain why S, B, A, T are concyclic points. For the same reasons as Part 1, angle QBS can be shown to equal 90 degrees, and points B, Q and T are collinear, which means they lie on the same line. Hence angle TBS equals 90 degrees. Now points A, T and P are also collinear, and we've shown from Part 1 that angle PAS equals 90 degrees. Hence angle PAS equals angle TAS, which equals 90 degrees as well. I've sketched a diagram to help visualize what's going on here. Here is interval ST, here is angle TAS and angle TBS, and they're both 90 degrees, both equal to each other. So if we let ST be the chord of a circle, then the angles TAS and TBS subtended by chord ST are equal. And because they're equal, that means STAB must be points on the same circle. Therefore, SBAT are concyclic points. Part 3. Show that the diameter of the circle through S, B, A and T has length A times the square root of p squared plus 1 in brackets times q squared plus 1 in brackets. ST is the diameter of a circle since angle TAS, or angle TBS for that matter, equals 90 degrees. And the reason is angle in a semicircle is 90 degrees. So using the distance formula, we have ST squared is equal to x2 minus x1 in brackets squared plus y2 minus y1 in brackets squared. So using the appropriate coordinates, we have ST squared is equal to A times P plus Q in brackets minus 0 all in brackets squared plus APQ minus A in brackets squared. Now we can discount the minus 0 here, so we get AP plus AQ, and we get that by expanding this expression here, and that's in brackets squared plus APQ minus A in brackets squared. Now we can factorise out A from this bracket here and also this bracket here. And when we factorise it out, it becomes A squared. So ST squared is equal to A squared times P plus Q in brackets squared plus A squared times PQ minus 1 in brackets squared. So we have a perfect square expansion here and here. And that gives us A squared times P squared plus 2PQ plus Q squared in brackets plus A squared times P squared Q squared minus 2PQ plus 1 in brackets. So we can expand the brackets here and here. We can factorise out A squared here and here as well. So combining everything all in one bracket with the A squared on the outside, we get A squared times P squared plus 2PQ plus Q squared, that's from this bracket here, plus P squared Q squared minus 2PQ plus 1, and that's all in brackets. So we have a plus 2PQ here. We'll cancel with minus or negative 2PQ here to give us 0. So we're left with ST squared is equal to A squared times P squared Q squared plus P squared plus Q squared plus 1 in brackets. Now we have an expression inside the brackets that consists of 4 terms. So we can factorise by grouping in pairs. I'm going to factorise P squared from these 2 terms and factorise 1 from these 2 terms. So we get A squared times P squared outside of Q squared plus 1 in brackets plus 1 outside of Q squared plus 1 in brackets, all in brackets. So our common factor is Q squared plus 1 here and here. So factorising that out, we get A squared times P squared plus 1 in brackets times Q squared plus 1 in brackets. Now we need ST, or the length of ST, not ST squared. So in order to get ST, we need to take the square root of this expression here. So the square root of A squared is just A, and the square root of P squared plus 1 in brackets times Q squared plus 1 in brackets is just the square root of that. Therefore, the diameter of the circle is A times the square root of P squared plus 1 in brackets times Q squared plus 1 in brackets.